Good afternoon. Okay, lecture 24, classical oscillator and resonance. This is of all of the subjects that come up in classical or quantum mechanics, those that involve resonance are representing the single most important phenomenon that we know of in all of physics, bar none. Now I'm talking about resonances that are as large as the Earth and the Moon system, or a black hole, which apparently have waves that resonate too. But let's just be practical and think about our own bodies. Listening to hear sound requires very high quality resonance, tiny little oscillators, oscillating cilia on the cochlea. For me to talk to you, I have to resonate a vocal cords, more like a little blob, but in mine anyway, I have a very good voice. But that is the way I transmit information to you, and then you have your ear. So far, I'm not deaf and you're not dumb, but in order to see, you need really high quality resonators and chromophores for your eyes to amplify incredibly weak signals that are coming to you. So that's what we're talking about today. We're going to do the theory of that from Newton's equations of motion, basically, classical stuff. But the classical stuff follows the quantum stuff, as we've said many times in this course, and we'll continue to do so, particularly tomorrow for that seminar, where we find that resonance is at the very core of everything that happens in relativity and quantum mechanics. The waves that oscillate resonate themselves. And so this is just the beginning. This is the Lorentz theory of oscillatory motion that's being forced, that is resonated. Before we get to that, though, we'll be going back to some very simple stuff that involves just the linear harmonic oscillator without anything doing, which is going on the screen right now. I'm talking about that phasor diagram there. But I'd like to show you a couple of things that are not normally given in a description of Lorentz's theory of classical harmonic resonance. And that is figures of merit. They're called the 5% solution. That's something that once you learn it, you can figure out a lot of things that happen with resonance in your head. You sit down and do complicated calculations. Simple arithmetic is all you need. Also, the quality factor. Our quality factor is different from others by 2 pi, and that's important for what we'll be talking about. Now, the more advanced stuff of this involving Green's solutions, we'll introduce that a little bit as well. And the Green solution for the forced damped harmonic oscillator, this thing, I hope to get to a little bit of today. If we rush, we can cover the whole thing. It's probably not a good idea to rush such an important subject, so we'll take it in time. And of course, as always, any questions, you have to stop the professor when you don't understand. So this is the basic mathematics of the Lorentz theory for the forced damped harmonic oscillator. We're going to take that apart. We're just going to do a harmonic oscillator, and then we'll do a harmonic oscillator that's got a little bit of friction, and this is one of the few times in this pure classical mechanical course that we actually talk about the messiness of friction. Fortunately, it's not so messy here, and it's, of course, idealized. But then finally, when you put the force on, when you are going to apply a tiny, weak, stimulating force to this thing, what happens? That's the idea of the Lorentz theory, is to explain that. Now this is just the Newton mass times acceleration equals the total force. And these are the three terms of the total force. We're going to go ahead and treat each one in turn, starting with the just plain restoring force, the thing that brings the oscillator back to center. So you have to have some force or some acceleration. I'm going to clear the mass out of that equation. So this is units of meters per second in acceleration. In this case, it's going to be a constant, which will have some meaning later on. It's the oscillator frequency squared times the amplitude. So this is a very famous harmonic oscillator equation that every physicist has seen many times by the time you've even got a bachelor's degree in the subject. The idea of having a force that's proportional to z goes back to Newton's nemesis named Robert Hooke. Hooke's law is the first approximation to the distortion that you get in any system that's stable, and that is that your force that you have to apply to get a given distortion, if the distortion is small, is just linear in the it's linearly related to the force that's needed to achieve that distortion. So Hooke's law is generally thought of as something that you do to a spring. You start with no force at all, then you push the spring. Either way, there's always a force that is negative, that is resisting your distortion. And that is up to a point going to be proportional to how much your distortion is. So the reason this equation is so important is that most of the oscillations that we talk about are small in amplitude compared to what the system would need in order to be broken or destroyed. And therefore, just about any stable object will ring if you hit it. And if it's a stable object, it will just ring, and then the ring will die off. We'll describe that here. And everybody will be happy. You go too much bang to it, and you're getting the other terms in this thing. You take the thing apart. Now this is true of quantum atoms, quantum molecules too. The waves run around in there to make us think that the atom has a spring.
I have a question.
To the,
when you say that when you hit too hard, you get the other terms, is it some kind of a series expansion?
well, you remember that we've already talked about oscillators like the pendulum, and that if I just do a small kick, then I have pretty nearly a harmonic oscillator. That's already too much for most people. That would be only a two-figure at most harmonic oscillator. Most likely I'd be talking about something like that, right? Then I would have it correct to maybe 3 or 4 figures, right? Because this one's force changes as we come up. So does everything else. But the idea is that that force, however complicated, around the stability regions, and remember what we were talking about when we did the effective potential? The idea is that no matter how crazy the effective potential is out here, that little valley that it lives in, okay, can be the Alps over here with jagged peaks, but in the little valley, it's parabolic. You see, the only other thing it could be would be a line like this. Well, that's not a stable point, right? You got to move until the line is horizontal, and then the only thing you see around it is a curve called the parabola, which is the potential for the linear force z.
So for any small displacement, we can approximate the potential to be parabolic and model
The
it
potential parabolic, that's a Hooke potential, and the force law, the derivative of the potential is a straight line. Does that answer what you're after? Okay. So we're going to just redo the basic dynamics of a harmonic oscillator, which involves this little gem that we've seen already several times. That is the basic idea that e to the I something is cosine of the something plus I sine of the something, or you can put a minus sign on it if you want. Actually, we do want to do that. It's very traditional to, at least in this laboratory, but it should be everywhere, have the phasor be a clock. And the reason that it is a clock, that is the reason it is going clockwise, as you can see on the animation there, is because we're plotting the position on this axis. That's called the real part of a complex amplitude. And if you saw this Z, you know we're in for complex bookkeeping. Very convenient, as we explained in Chapter 11 of Unit 1, all the conveniences that come with a complex function or arithmetic. And this part, the real part, the cosine, which is being plotted on this screen here, and I'm just going to go ahead and let this thing start over. And I have to be careful because this is an old program going on a fairly new computer. But if I just redo that right there, I should get what I want. So here's the phasor going to a certain point, and you see the cosine part being plotted. Actually, it is a sine because I started it at 0, but I can start it anywhere. I could, for example, take the thing to the center, let the time run a little bit, and then start it out right here. Just bring it right up here and start it there. So I would make a cosine from that point on. And there you see it. And it's going to just go the amplitude I gave it. So this is a simulation of, you know, what would be a nice toy. It'd be a big sphere in the middle of the room, and you'd push it off center, and it would oscillate with the amplitude you gave it. So that's the position being plotted, and it's direct. You see it's following it. The real part is up here, and that's the way it's going to be in all of our discussions of waves later on, and including the seminar tomorrow. I put the real axis this way. It's traditional to put the real axis this way, imaginary axis up. Imaginary axis is basically plotting the velocity. Now I give it cute names. The real part is the is, and the imaginary part is the gonna be. That is, for Clinton, you is or are doing something bad, and you're gonna be in trouble. That is the political side of this, but the basic idea is that when I'm at the very top here, I have no position at all. I'm at the origin. I'm passing through my initial or my resting point, and up here is positive velocity. So the only direction I can go is this way. So all phasors of the normal classical type are going to be left-handed, which is clockwise. And that's very against the engineers. The engineers always treat this as positive, and they use a positive sign for anything that has time attached to it. So be aware of that if you read about complex numbers in various parts of your textbooks. They usually screw that up rather badly, is my opinion. Okay, so let me just pause this thing for a minute, and we'll go through some of the algebra without the distraction of the hypnotizing phasor there. What I would like to show here, and this of course is a picture right out of the textbook of the phasor at various places. Now I have here a pretty fine scale. The one that is shown here is a bit coarser. It probably might not hurt for me to change the animation to make it look more like this. But here you can see pretty clearly the real part of the thing starting out there with a right at 0. So this would be a sine wave right here, not too different from what's over there, but spread out a little bit, giving the time clock a little more speed. So let's see. What we're going to be talking about for the next few, well, in fact, really the whole lecture, is the famous 1 Hertz oscillator. This is the thing that goes at 1 Hertz. That means one a cycle per second. And in order to give it the professional, shall we say, name for its phasor angular velocity, you have to bring in the very famous constant pi, and this is an angular velocity, omega. I like to think of it as W, so this is the either winks per second or wiggles per second or something like that, but it's 2 pi, that's 6.28, and lots of digits forever, radians per second. So radians per second, angular velocity or frequency, is the professional way to handle, and that's because of this exponential here, which demands that we talk about radians. That is, the things that are the independent units for a sine and a cosine. We are talking about a circle, and that's a clock, a very physical and geometric idea that we need to, always use. So we have that particular thing that just involved force. Now we put the friction in. Okay. Well, we have kind of a, nobody has his name on this one. It's not hook. It's just sort of a sloppy thing we do to account for the chaos that's involved in any frictional system. We just say, okay, well, the first thing is something that's linear in the velocity. So we have a B coefficient. We're going to later name that 2 gamma. Actually, 2 gamma times the mass, because the mass has already been divided out of this. This is the force over the mass. That particular frictional damping force is the thing that's going to be affecting this oscillator. And it's important to see a couple of things about the damping force. So I'm going to go ahead and run a simulation just so you can see. It's quite pretty what happens to a damped oscillator. And I'll start this thing up again. Now the damping is controlled by the coefficient gamma. This is a very conventional notation for this B coefficient, B over M actually, coefficient. And we'll see why that is when we go through the algebra. We don't want to carry a 2 around in the algebra. We get rid of it fairly early in the game here when it comes to solving a quadratic equation that has well, you'll get to that. We'll see that. Anyway, that's just a convention. But I have it actually in the program right here. If I give it just a little bit of friction, say 0.1 or 0.2. We'll go ahead with 0.1 there. I think that should do it. Let me see if it'll actually change. That's 0.2. It doesn't seem to be working. Why is that not happening? That's weird. Let's try it. That is gamma. And it just, because it's multiplied. I'm a very fancy programmer in the old days, and forget that I have 3 ways to enter a number here. And this is the linear way of doing it. So I'm going to put this at 0.1, just to put a little bit of damping onto this thing, see what happens. So it starts off like a oscillator. Doesn't look like it's being affected much. That is a small amount of friction. This is a fairly high quality oscillator. But so we didn't quite make it home on the way around there. And in fact, there's a little yellow line there that represents a decay of the oscillator. It's an exponential function. So it is decaying very much like a radioactive isotope will follow the same curve, and this is what's going on in the radioactive isotope from a certain viewpoint. Okay. So this is the damped oscillator. Now it's the forced damped oscillator that we're really interested in, and we'll be using damping of that of this yield 0.1, 0.2 in our discussion. But you can see it slowly closing in. And I apologize for the X-boring that's going on. That, you know, something, this is one program we haven't gotten on the web yet. And of course we won't have that when we get it on the web, and it'll be a lot more fun to play with than this one on modern computers. So that's what we're looking at here. And here's how you would solve this thing. What you do, this is the trick for all sorts of differential equations that have this symmetry, and that is this, they're only constant times powers in derivatives. You know that the derivative of an exponential just gives the exponential back multiplied by the coefficient in the exponent, and that's what's happening here with this particular exponential. It's giving us back a imaginary thing on the first derivative, then a minus sign for the square of the imaginary on the second derivative, and that's the equation that we're going to solve. So the usual trick for solving a differential equation is being carried out here. And then we have this differential equation reduced to algebra. We have no force over here, so we're going to be able to solve for the actual frequency of this oscillator. Now it was 1 hertz before, and I'm looking at it right now, and it seems to be going through the tick marks every time. I see no slowing down of this oscillator on this graph, not to within a pixel or so. There it went again, right through that tick mark, you see? So 1 hertz oscillator with some damping is enough to reduce it by, well, at least 20%, down to about 80% reduced as we go by the 15 mark there, and again, we go right through it. So one of the things you should remember is that small amounts of friction don't seem to really hurt this oscillator, even though it really hurts its amplitude. It doesn't hurt its frequency, and frequency is what you're looking for in a clock. So it's not changing its value as a clock, at least as much as we can see from a crude graph like that. Now in Evenson's lab, they're working not with 1 or 2 figure accuracy, but with 9 figure accuracy. That was kind of a record in the day. Absolutely astounding record, in fact, at the time.
Dr. Harter, I have a question.
Yeah.
When there is damping, damping reduces the amplitude of oscillation, right? It doesn't
like
affect
that.
Yeah. So is there a case where the frequency of oscillation is also affected in addition to amplitude?
Well, let's calculate how much it is affected. We're kind of seeing it right here. This is a thing that's just going to affect the amplitude because it's imaginary, but the frequency that you're talking about is omega 0 squared. We can take that 4 out, right? Minus gamma squared. Now you see why I put a 2 on this, so I didn't have to carry that through as a half. All right? So the actual frequency that you've got there is omega 0 squared, that's the 1 hertz, minus the square, okay, of the gamma coefficient, which is 0.1. So it's only affecting it 0.01, 100th. By the time we get to the end, we have to go about 20 more before you'd see it, right? So it's only affecting a 3rd figure, or maybe 4th, depending on how you count. Okay? So there's the actually answer written out in a more clean way. That's the thing that we're going to stick in this exponent right here. You see, that's the value that comes out of setting this thing in this differential equation, getting an algebraic equation which gives solutions plus or minus this thing. That's just that it's telling us, hey, you could have run your phasors the other way. We're only going to take the minus on that one by convention. Okay? So the whole solution is e to the minus I times this thing with the plus or minus left in there. It'll look like that. So it's e to the minus I gamma t. That has a big effect. The exponential drops this thing very quickly. We have to get a figure of merit for that. But the frequency, omega gamma, not so much. And that's the point I want to make here. It oscillates at a reduced frequency, but only slightly, about 0.05% from omega 0 due to the damping of 0.2. This was double that, which we'll show in a minute. We'll run this thing again. So you work it out, omega 0 squared minus gamma squared, where gamma squared over omega 0 is this ratio here. So what you're getting is 6.283185, that's pi, 2 pi, minus 0.003183. So you're dropping the thing to 6.802. Let's go ahead and run the 0.2 damping and see if we can see it by the time it gets off the graph. I'm going to jam this thing up to 0.2 here. That's 0.2, isn't it? Yes, and let's just erase everything and start again. Still going to be 1 hertz for as far as we can see. But now you can see, by 15, you can hardly see the amplitude down there. But notice it's going through the tick marks on the upswing and the halfway point on the downswing. And then back through another tick. This time 2 seconds have gone by on their scale here. Time's very slow in here because this is a boring lecture. And here we now 3 seconds. Okay. Now I've slowed this thing way down because you really want to see all this mechanics that goes on inside a resonance with enough time for you to figure out what's going on. It's a stop motion sports here. So that is the thing that I wanted to make a point about on this particular oscillator. So this is what it looks like if you don't XOR. It's a Archimedean spiral. I'm sorry, it's a logarithmic spiral, very close to a logarithmic spiral because of the exponential. It's just that I was fooled by looking at the thing. It looks to me like, you know, a linear thing, but it isn't. It's proportional. We'll be seeing an Archimedean spiral with the force part of this story. Okay, and again, that's out of unit 4, chapter 2, the figure that's there. And I encourage you to read all this stuff. It's one thing to really learn it by wrestling with it, and I'll be giving you some problems on this. Now here's an easy way to tell you know, how much we have after a given time for a decaying anything. That's an exponential decay. So many things do this because so many things are geometric in nature. See some more examples tomorrow in the seminar. Figures of merit that I'm interested in. I noticed this early on when I was teaching this for the first time, that the usual thing that they do is say, how long is it before you've lost half? That's called half-life. I'm more interested in what would probably be stockbroker's concern. If his capital were to be reduced by 95% to, he had 5% left, I think he would call himself broke. This is what you should remember is that e to the minus 3 is 5%. That's the little thing. Now, if you want to be really precise about this imprecision that we're getting from the damping, you can go e to the minus pi. And e to the minus pi is really interesting. It's 0.04321. So if you want to carry this out to 5 figures, that's something even I can remember. I can count backwards from 4. Okay? So you know it's less than 5, well, it's 1 less, and then you tack those on. Okay? So if you really want to be precise about this, that's what we'll be doing. And we'll point that out a couple of times later on. But right now, I don't want to mess with all those digits. I'll just go 3. So here's the 5% time. 3 over gamma, 3 over 0.2 in this case. So when that thing got down to 5% of its original amplitude, it was 15 seconds. And that's what we're talking about at the 15 mark here, right? But still, you don't see the frequency moving even a pixel. Okay? So that gives you a little bit of a, you know, this is the kind of stuff Tesla did, I think. I mean, he was considered a genius because he did look at some piece of rotating, oscillating machinery and put a chalk mark somewhere and it would be right. And this is, you know, this kind of tricks help you do that. Now, as I said, more precise, e to the minus pi, 0.04321. Okay? Well, then if you want to work it out, it's not 15 seconds, it's 15.708, okay, to get the, you know, down by that factor, the minus, e to the minus pi. But pi is part of this, you know, our phasor, so you know, you run into situations where you want to know that blue thing instead of the black thing. Okay? All right. Now, here's another thing that you should always remember, and that is the number n of oscillations to reduce the amplitude to 5%, okay, is, well, what's your angular frequency times the 5% divided by 2 pi, okay? Well, that's 3 omega sub gamma. See, this is the full frequency, which is almost the same as omega 0, divided by 2 pi gamma, okay? Now, if 3 can be canceled from pi, and this is why I would like to use this one, but I don't want to carry all those decimals, so I won't. I'll just say it's very close to omega gamma over 2 gamma. In other words, it's the frequency, omega gamma, that we get when we correct this one, divided by this coefficient. That is the number of oscillations that you're going to have. Well, in this case, when we have only one oscillation per second, it's the same answer we got before, but this is what you can do with any frequency. Omega over 2 gamma will figure later on in the forcing problem. And it's true for all frequencies. And you might as well make it omega 0 if your gamma isn't too high. It's a good working relation for high quality oscillators. And certainly for super high quality oscillators. All right, well now we're about to really put the screws to this oscillator, so to speak. We're going to have a stimulating acceleration here due to an oscillating force. But in general, it would just be any function of time. So that's where Green's functions and things like that come in. We're going to do the simple thing first. So this is where we do the real problem. That is, how do you resonate things and how well do they respond and all of the figures of merit that go with that. Okay? So here's what the differential equation looks like. It's got all these terms. The damping terms we just discussed, and before that we discussed the restoration, and now we got something over here called the stimulus. Now I've taken the mass out, so force over stimulus is acceleration. This is the acceleration of the stimulus. If it's an electric charge that's being hit by an electric field, that's a force that's equal to the charge times the electric field. So it'd be E over M, that's the famous Thomson ratio, multiplies an electric field, if that's what we were doing. And of course, in this laboratory, we're very interested in spectroscopy of solids, and I'm interested in molecules, and there are people interested in atomic structure. That's what you're doing to an atom. It's a blob of charge, as far as the classical version is concerned. You come in with some electric field that's swish, 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 and if that electric field is pretty close to some transition in that atom, well, then we might be talking business here about a resonance that would make that atom excited, and it would proceed to radiate and send light off in other directions. That's what spectroscopy is really all about. And we're doing it classically, you see. This is what you should be knowing before you worry about the details of the quantum things. There are entire books, in fact very good books by Sigma is one of them, where you learn just about all there is to know about functioning lasers using Newton's law, this stuff. So you should be aware that that exists if you're going into the laser business. And it's only when the laser gets to be low in amplitude that you start worrying about the quantum effects. Then all hell breaks loose as far as, you know, the laser's actual performance becomes chaotic. Okay, so this is the equation we want to solve. We want to solve for z. So I'm going to take this and put it in the denominator. What are you talking about? You don't do that in calculus. That's illegal, right? No, you can do it, provided you can take an inverse derivative. You can do that. And with an exponential, it's no problem at all.
Dr. Harter, what is meant by inverse derivative?
That's a pretty crazy question mark here.
What is meant by inverse derivative?
I don't mean the integral. That's operationally speaking inverse. I mean just plain old first grade 1 over. Doesn't sound okay though, does it? I mean, this is not something you were taught to do, right? But for an exponential, you were taught how to do this. Now let's just go back to this equation. We're doing the same trick. We're going to substitute z with an e to the minus I omega something, right?
Yeah.
Then you can do it, right?
Yeah, that is it. Yeah. Take a trial solution of the form e to
Exactly.
the lambda t and then.
Yeah. Not crazy if the stimulus is not an exponential, because the derivative of an exponential is just the exponential all multiplied by the coefficient, right? The rate. Okay, which is imaginary in this case. Okay? Or complex later on. I think the whole thing there is going to make it complex. Okay? So this is where the bookkeeping associated with the complex numbers is saving me about 2 or 3 screens of manipulations and screwing around. We just write the answer with this very powerful bookkeeping of the exponential. We just write that. That's it. Now, of course, I have to work this out. I got to know how to get those imaginary guys up off the denominator and into a numerator expression as a real and imaginary part. When we've done that, we're done. We have solved this problem. But I want to make sure that you see this first, because this is the heart of the Lorentz theory. This is the front piece, you might say, of that. Okay? It's also the heart of what we call Green's functions, which invert differential operators in many dimensions. We used to have one dimension here of time, and in the degree of freedom that we're talking about, the amplitude is being solved for. So this, if I just have a monochromatic source, that's what this is, a stimulus, omega s, is something, if I had a dye laser, I can literally tune this by turning a knob and try to resonate an atom that may or may not like that frequency, and we're going to make a discussion of what that means. Okay, so there's the Green's function solution for a force damped harmonic oscillator. As I say, this is really the end of the lecture mathematically, but we have a lot more to say about this. The way I like to draw it sometimes is, here comes a stimulus, and this is a lot of this stuff is done by Jewish people, and some of them know Hebrew. Hebrew reads from this side to that side. That's why your quantum mechanics always has the initial state over here, then some operator that gives you a final state over here. So this is a classical rendition of that sort of Hebrew way of looking at a stimulus comes in, gets multiplied by the Green's operator or function, and out comes a response. Okay? Stimulus and response. Fundamentals of ideas of psychology. If only we were really simple, and I think maybe this might work on some of the members of the Tea Party but most people are more complicated, you know, your Green's function can be crazy. Okay, so here's the deal. What we're interested in is the real part of this thing. That'll actually tell us what the amplitude is. But we're also going to get some information about the imaginary part of the response, which is the kind of the velocity. So we're going to be working in phase space, as we always do. So I need to know how to take 1 over a complex number. And we already went through this in chapter 11. But what you do is you multiply numerator and denominator by the conjugate of this so that you get a real thing in the denominator. And then you end up with this thing, which is the same as this thing, but with a sign change on the imaginary part. So that's all I'm going to do. And that gives you the complete real part solution, real and imaginary part solutions to Green's way of doing this. But you know, H.A. Lorentz did this, you know, in one way or another, just as well. And there are two ways you can do it. Just as there's 2 ways to regard a phasor, I can regard the phasor using the real and imaginary coordinates, okay? Or I can use polar coordinates. I can measure the amplitude and the angle. So this is the polar way of doing it. And then there's an angle associated with this Green's function. And that's called the phase lag. And I'll explain what that is by showing animations and comparing it to what this does with the mathematics. Okay, so you know, here is a picture of what we're going to see. We're going to see the stimulus as a phasor that's colored red on that clock diagram going around at the stimulus frequency. Okay? Hopefully it's going slowly so that you can follow what's happening. And then the response that you're going to get, at least from this part of the solution, and this isn't the whole solution yet because initial conditions have to add on and say, well, where did you start this thing? Because this is forever. And you want to start at 0, then you'd better have added already something to make this whole total solution 0. We'll talk about that later on. But in any case, there's going to be a response that usually lags behind the stimulus. Okay? It's going to look like that. Now, it may get real big if you're on resonance, but it may also oscillate, do all kinds of crazy things, but it will be behind the stimulus most of the time. Every once in a while, though, we're going to see it because of the initial conditions, you know, oscillate around the stimulus and then damp in on some particular angle. That's that angle that we're headed for. That is the phase lag that you ultimately get when this thing settles down. So that's just stating what it is that you need to know and that we need to talk about for this oscillator. So anyway, here's the real part of this Green's function. That's this thing. Here's the imaginary part of it. In that rotating frame, it includes the stimulus, you see. That's going around as shown there. And then the angle, actually angle with the stimulus, is the polar angle, and this is the radius that you've achieved at some a later time when this thing settles down. Okay? So that's just showing you where the polar angle appears in the algebra and in the geometry. Does that make sense? Well, we probably have to see a few examples to get the picture here. And they're quite spectacular. Now, before we do that, I thought we ought to just plot these real and imaginary parts. And what you see with the imaginary part is what we usually see in ordinary spectroscopy, is that you see that nothing's happening, nothing's happening, nothing's happening. I'm turning the frequency up on some laser, and all of a sudden, whoa, I get this big glow coming out from some potassium atoms in a bottle or something like that. And then I go at a higher frequency, it all dies out. Okay? So this is called a spectral line. All those little pictures of spectra that you see going back to the time of Fraunhofer looking at the sun, and he would be seeing it inverted because it would be absorption of spectra in the vapor of the exterior to the solar corona. And every one of the sodium atoms that's up there is singing its song at different frequencies to tell you, hey, I'm here on sodium. Boy, that was a big breakthrough in the 1800s when that happened. And we still looking at the sun and trying to figure out what's going on. But there's not just the imaginary part, which is fairly simple in comparison to the real part, the blue real part, which starts out non-zero. Okay? And then it goes, and it's taken off for the buckwheat until right about here, right in a very important region that we call the resonance region that says, hey, I'm not going to do this. I'm scared. I'm afraid of heights. So I'm going to just go to zero. And where it goes to zero is the actual fundamental frequency of this resonance. But he's going so fast, he falls all the way down just as far as he got up, and then he turns around, hey, I was really scared there, but I'm coming back. So he comes back on the negative side, and then goes very quickly to zero. So that's the anatomy of the real and imaginary parts of the thing. Now, the real part is really hard to measure, but it's also, when you learn to do it, very telling. This is the one that gives you information about the dispersion and the refraction of the light wave in the region of the resonance. Most of the time, the index of refraction is constant. And this is a very reduced scale. I mean, this would go all the way down to Fort Smith, and then as you cross the river, it would go up, say 50,000 or maybe more than that, come back down again, and then back up again, and then it would be zero as you went south of Fort Smith. I mean, that's the scale that we're looking at when we talk about typical atomic and molecular spectra. Enormous pieces of resonance that are responsible for us seeing. Okay, we need that in order to get the huge amplification that you need to actually be not blind. So these two functions, particularly this one, play a really big role. Now here is a figure of merit that's really worth remembering, and it involves that number I told you about, the omega 0 over 2 gamma. Remember that thing? Okay. What did it tell you? It told you the number of heartbeats in a dying oscillator. That's what this told you. Here it tells you something else. It tells you the resonant response over the zero frequency, what we call direct current. That's DC response. That's an old terminology that was distinguishing, you know, the Thomas Edison type electricity, which was DC in New York City with all wires so thick that you couldn't even see the sky, and AC, which is what Tesla was trying to sell to Westinghouse and all those guys. Finally, Morgan Chase gave him some money to hang himself. But the basic idea is that the resonant response is going to be, and Tesla knew this, very high for pretty low frequencies, and that you'd be able to send power across the river from New York, maybe down to New Jersey, and then finally across the whole damn country. So that's what we're looking at here, is a ratio of this tiny little DC response to what you get when you really hit the frequency. Okay? Now remember what that number was for our oscillator. It was the number of heartbeats that you got till you got to 5%, right, which was 15 heartbeats, right? That's its lifetime, 5% lifetime, okay? Well, that's what we're going to get here, is an amplification factor of 15. There's 15 of these to make that. So that's not a coincidence. That's what the mathematics tells you. This is the resonance Green's function. That's the DC zero frequency Green's function. They very simple when I set this thing equal to 0. Okay, and set the omega s equal to omega 0. Okay, we got an omega s here squared there, you see. I come up with this thing and over this thing, and that's just omega 0 over 2 gamma, which I call the angular quality factor. This let's distinguish it from something that has a 2 pi in front of it, which sort of clouds the issue here. We're talking about you know, how many heartbeats we got, not how many radians the heart does. Okay, so resonant response, DC response, 15:1 ratio. That's you know, really important. Now let's just look at a couple of things. We did a gamma equal 0.1, right? This is what we're going to do shortly here. I guess we might as well go ahead. Let me look ahead here and see if I have a picture of what it is we're going to get. Maybe we ought to look at this before we look at the picture, because something really weird is going to happen, and I've got to explain it. Here is the whole solution. What's called the inhomogeneous solution being added to the homogeneous one. Now this is using a nomenclature that comes from various classical field theory, particularly electrostatics. This term here is adjustable parameters. Actually, it has 2 adjustable parameters because this can be complex. So there's 2 numbers you have to specify in a second order differential equation. You have to specify where it is and how fast it's going. In other words, you have to specify its initial phasor pointer. So this thing is the initial phasor pointer that we're going to set wherever we want. And then, of course, that initial phasor pointer is going to get damped out, finally to 0. But while it's being damped out, it's going to run at the frequency the oscillator wants to run, omega gamma. Exactly. Okay? That solution, plus the one that we just worked out, which is Lorentz's response solution, makes a total package. But this one does not have any adjustable parameters in it as far as setting initial conditions. All it has is how well are you going to be able to tune omega stimulus, how close are you going to be able to get to the target, which is omega 0, okay? Not omega gamma. Omega 0 is what's at the center of that thing I pointed out. And then, of course, you can change the amplitude too, but don't do it. It'll screw this thing completely. But if you do want to do it, wait, and then finally it's right again. And then there's this phase lag. That's totally a function of where your omega s is with respect to your omega gamma. This phase lag right here. Okay? So these 2 are the part of the solution. This is not a function of initial condition. It marches to the stimulus only. The stimulus determines it, and then it uses the stimulus frequency and lags behind it, right? That much on the road. Okay. Meanwhile, this one lets you set the initial values or boundary conditions to this whole thing. If we didn't have that, we can't set anything. We just have to take what we're given. Does that make sense? Now this is very simple when you use Green's functions for field theory, right? You got to set the boundary conditions with this solution, and then the Green's function will just tells you what all the various stimuli, that is charges or currents or other things, are there.
But
and what they're doing.
We have written down the Green's function in momentum in frequency space. It's a function of frequency.
We are essentially working in frequency space here.
But how do we?
It's a Fourier transform.
So, but then it's hard. How do we write down the boundary conditions in frequency space? Because it's
boundary conditions are boundaries in time here.
That's right. Yeah.
Right? And we specify it entirely at time equals 0. Now what we could do is say, I want to be such and such at time equals 0 and something such and else, and just talk about position at a later time. That would be a you know, 2-sided boundary conditions for time.
So which means we work out the problem in frequency space, take the inverse Fourier transform, and then apply the boundary condition.
Essentially, we've already done the Fourier transform because we've only got one frequency, right? Now, the Fourier transform comes in when you say, oh, I've got a whole Fourier series going into this thing, right? It's a linear equation, so you just add them up. So you get a Fourier series for the response. Then you've got to put this guy on here to make it right. That means you've got to have just the right thing to take care of all these guys and make what you want initially at time equals 0. When time equals 0 is you've still got this thing, right? That's what makes it, the arithmetic difficult. I mean, lengthy if you have a lot of them. Now there are tricky ways to do this in the continuum of calculus, but we're going to put that off for a discussion to possibly later. Okay? Now this one is also called the transient solution since it dies off. And the other one is known as the steady state solution since it's present as long as the stimulus is. So my human analogy, anthropomorphic analogy to this is whenever you get up, you wake up, right? Where am I? God, what did I do last night? Jeez. Right? And finally you stagger out of bed. Oh, jeez. Okay. Now I'm in steady state. Transients are gone. Okay? That's what this oscillator is going to do. So that's why I said we better discuss this before we put the screws to this thing. Okay? So, well, I can actually go ahead on this one because that's kind of what we're going to see. We'll see more interesting things as we turn the damping down. But that 3 over gamma for us, 15 seconds, that's how long it's going to take to get to the steady state solution within 5%. Because the transient is the thing that dies off after 15 seconds. Okay? So from here on out, it's going to be Green's function. So that's why most people don't even worry about the transients, because, you know, it's gone like that in a laser situation. Only in really fancy types of picosecond pulsing do they ever have to do that. And then they really get some singing. Okay, so let's consider some examples, particularly interesting ones like that. Now the way this program is set up is unfortunate, but I'm going to have to play around a little bit to make this work right. If you eventually will have something like this on the web, but it's going to take a little bit of doing. You've got to realize this is just Macintosh world here that I was dealing with. I've got little buttons here to push to see you know, what happens at various frequencies. And what I'm plotting there is just the total, the magnitude of the response that we had in this plot. I'm wondering why that thing is doing that. There's something that is weird. I usually turn it off when we've got a charge hooked up to it. It shouldn't do that. But this response function consists of the real part, which does this turnaround here, and goes through 0 at that point, and the imaginary part, which makes the what we'll find out later is a curve called the witch of Agnesi in old calculus books. What we have is the magnitude, which is the square root of the sum of the squares of the real and imaginary part. That is the length of the phasor, which is this dark line right here, we say. And it's a little bit wider than the actual imaginary part that we call the resonant region, and the inverse lifetime of this object. So that's what's actually plotted right there. It looks like a witch's hat. For I guess there are a lot of witches around that had hats that look like that. Otherwise, we wouldn't have this name. But this one is a little different from the pure witch of Agnesi, and then it's lopsided. It's got a DC side to it. The quantum witch is called the pure Lorentzian, and it's a very tame thing that is very symmetric. We'll see pictures of it later on. We've already seen pictures of it when we looked at the function 1 over z in the complex variable discussion of dipoles and monopoles and all that. So let's go ahead and make a few of these. And the trouble is that with the computer the way it is now, you're going to get a blur for those things. But we can at least look at this side of the picture and see what's happening. First of all, let's go with a very low frequency. Now, when I set that thing, it immediately gives me a del t here that I don't want, and it's way too fast. So what I'm going to try to do is lower that to at least a 0.0. Now what's going on here? I'm adding a minus 0.09 and 0.1. I should be able to do that. That's getting me, I'm going to keep doing that. Well, that was too much. Now let's bring it back here. If I do that, it'll just stop. There we go. And then I'm going to change the power of this thing to -3. Let's see if I can do that. And take away some of that speed of the computer. There's 0.008, 7654, 2, 1. Very clumsy. Obviously we need to fix all this. Okay, that's probably not too fast. Let's see what happens here. Yeah, that's good. Now you can see what's happening a little bit anyway. So what this is doing is applying a very slow, almost DC, almost direct current, very slow frequency, which on that graph was way down at the left-hand side of the graph. And you can see that the oscillator is responding kind of weirdly. I mean, it went sort of with it, and then it's going against it. It's working out pretty well. And by now, we're at the 15 point, so within 5%, this is a steady state solution. That's all you're going to see from now on. You see, basically DC response. It's about 115, a little more than that because this isn't zero frequency, but not much. It's really not interested in playing games with this slow frequency. It's much faster than this. Okay, so that's what you're seeing there. Now, with a lower damping, let's see if I've got an example here. This one, with lower damping, you actually get some beeps during the transient. It can be pretty hairy. This one doesn't have ability to do that. We're not near enough the resonance to even have a possibility of that. We got to go a little bit further. We get the right computer here. We got to go a little bit further here. And instead of going back to this graph here, I'm just going to go up there and redo this thing with a gamma that's a little bit, let's see if I've got the omega stimulus, is what I actually want. I've only got 0.3, and the resonance for this particular animal is omega gamma is 6.28. We've only got a stimulus here of 0.3 compared to the frequency that omega 0 is right here, 6.28. So I'm going to go up, maybe get half of that. I'm going to crank this up to, let's see what I can get here. I can get 1.3 pretty easily. I can get 2.3. Let's get halfway to resonance, half the frequency. Let's try that, see what happens. That's fast, okay? Oh, it's just kind of waking up to that. Although it says, nah, I don't want to play. It is oscillating though at its at the frequency of the stimulus. Okay, at least it's settling down. And by 15, it'll be there. Okay, pretty much in phase though, right? Pretty much. How much is the phase lag at this particular point? It's written right here. 0.04 radians. I mean, it's right. It's basically just copying it. It's not lagging at all. Okay. So that's the thing that you want to see is as soon as it lags, you see, then you can put energy in. That's when you can do work on this thing. But if it's going to just follow you, you can't do any work on the thing. See, you can't punish it. I don't want to make an analogy with the Bush-Cheney regime, but basically the idea is how effective is the force, and it's not being very effective yet. Let's go ahead and go back, and I won't go all the way back to the control panel. I'll just go ahead and change the stimulus frequency here to something that's more near what the resonance would be. So let's fix it so it's only different from the resonance. And now that would be 5.3. If I do it again, it's 6.3. I don't want to go past the resonance quite. But let's just add maybe so that we're only, half of a radian per second off from the real thing. So I'm going to add, there's 5.4, and 5, 6. We're climbing a mountain here by doing this. We're going to be pretty far up on the resonant curve. So let's try that. Doesn't look like it's much faster, but it is showing some interest. Wow, I like this stuff. But then it said, oh no, I don't really like it very well. I'm not going to do this. But it's too late. The gamma's taking over. Okay, it's too late. You're stuck. And you're stuck at a very healthy phase lag. Okay? Well, a quarter of a radian, maybe a little more than a quarter of a radian. Okay? Radian's 57, say 60 degrees. You're not very far behind. So you can see him in there, how far he's behind, right? That's what we're talking about. We're talking about this response to that stimulus. And you can see his beating has sort of tapered off. The transients are gone at 15 to 5%, right? So we're making progress here. Okay. Now we're also pretty close to the end of the class. So what I'm going to do is stop pretty quickly here. I would like to take you to resonance, though. I mean, you've got to see that, right? What's the best I can do here? I can get 15 amplification, right? That's what we already showed. So I'm going to bring that guy in there as best I can with this particular control. I got 5.6. There's 5.7, 0.8, 5.9. 6.0, 6.1, 6.2, okay? And what else can I do? That's just a little shy of resonance, okay? So let's go for it, okay? Well, look at how the phase lag is almost 90 degrees. And that's the best you can do. That's the best you can do. Just think about what the force is doing to this thing. Every time it's maximum, it's past the origin. Come on, baby. And then come on this way. Come on, baby, this way. Come on, baby, this way. You see, it's always in phase and pumping energy into it. Look at it. It's increasing its amplitude. And now we're at 15, which is, we're within 5% of the resonant amplitude. We're within 5% of 15 times the DC response, which you remember is little guy there. All right? Now, let's take this to the extreme, just so you learn what this is really aimed at in terms of resonance in materials. Why can an X-ray see through you? The X-ray can see through you because we're out here in the tail of the resonant frequency of the highest electronic oscillation that's available for a particular atom, calcium, hydrogen, the various carbohydrates, oxygen that you have in your body, right? And then the bones have calcium, so they've got some really high frequency resonances in the electronic structure, okay? But once you've passed those, you're not going to get any response at all from the electronic oscillations at that frequency, say X-ray frequency. So the X-rays are going to march right through you without much change at all. And that's the way X-rays work, you see. All they get to see are some of the heavier atoms that have a lot of very high electronic resonances. And lead is particularly notorious. That will stop most X-rays. Go up into gamma rays and finally you're above those. The catch is if you go higher, you start getting the nuclei interested. Look out when that happens. But we don't have gamma ray lasers yet, so that is not something we worry about. In any case, let's go ahead and run this, but not at the high frequency that I get by picking the del T so damn high. I want to get rid of that. I'll try to lower that down just a little bit. That'll be good enough for government work. But you see what happens, it just dies. It's basically pi out of phase. That was too much. I still have to get rid of some of that. The computer's too damn fast. I mean, you got to realize that we started doing this in 1986 when the Macintosh thought the kilobyte was a huge amount of memory and 1 hertz was a real good clock time. So, we're doing the work of the Lord here. Let me make the power of this thing -3 so I can get rid of some of that there. I'm seeing here, I'm subtracting, there I could get a 0.01 if I wanted it. What's going on? The trouble is there's a limit to, let's see what I get when I do that. I probably did. That's okay, that's good. I don't know if you can see it, but the little tiny response is almost pi out of phase. So when you have a situation like that where you're pulling when you're zigging when it's zagging and zagging when it's zigging, that's a recipe for no response at all. And that's the situation with an X-ray when it's going through most of the atoms in your body, or in a piece of wood, or something doesn't have really active resonances at high frequencies. Okay. So just with that message, I think we've got the qualitative features and some of the quantitative ones of the most important effect in all of physics. Okay.